Hi, this is Chuck Benedict, mentor for Team 997, Spartan Robotics in Corvallis, Oregon. I thought I would do a video on automated testing for robot projects. I have a bunch of videos I recently did for vision processing, of which I did one on automated testing, but that was specific to that project, and I got so much feedback on that. I thought I would do one that's more specific to just a generic robot project, especially in light of the fact that we've changed over to VS Code as the integrated development environment. And also just because I have students tell me all the time that, the robot's not ready, they can't test it, et cetera, et cetera. It's all bull. There are so many tools out there that allow you to test your code without needing a RoboRio or a robot. It's not necessarily straightforward. It's not hard, but there are some things that you need to know, especially now that we're on VS Code. And with the test video, the video that I did on vision processing, I thought, well, let's just do one for vanilla robot projects so that those of you that want to help your students with automated testing don't have to do what I did, which is to kind of figure out all the little nuances. So we have a preseason competition called BunnyBot that we do here in the Pacific Northwest. It's held by a team called the Flaming Chickens. They just can't give enough kudos for the support that they give to the teams up here. This year's BunnyBot is supposed to be finding racquetballs and placing those racquetballs in our standard crates. And there's two different colors of racquetballs. There's red balls and blue balls. And you're only supposed to put your own team's balls. You're only supposed to take control of your own team's balls. So we are building a sorter mechanism that will intake the balls, make a determination as to what color ball we've got, and then if we don't have the right color ball, it'll eject it out before it is used for putting into our hopper. So I asked one of our students to build some code to run the prototype version of the sorter that we're in the process of building, and I did a code review for him. And in part of doing the code review, I suggested to him, hey, why don't you go ahead and write some unit tests to test your code? Because of course we don't have a sorter ready yet for him to test his code with. So I went on ahead and took some of the sample code that he wrote, did a code review, and put in an example for him to show him how to do an automated test, hoping that he will continue with adding more tests in. So I thought I would go over that code review process so that you could see what all is involved to get testing working on a iterative robot project. So first thing is to know is that his project, this is a standard WPI project that you create using the template. So there's nothing special about it. He created a class called sorter that extends from the WPI subsystem class, which is typical. But the first thing that he did, which probably a lot of people do, is in your subsystem, you're declaring hardware components that your subsystem uses. And let me go over to GitHub and show what he actually did. So the minuses show the code that he put in, and I think this is pretty typical. You put in your hardware components and you init them with constants that define the ports in robot map of where that hardware is sitting. The problem with doing this when you're trying to test is that you actually want to be able to factor this stuff out. You want to be able to mock it out so that when you're running your test, you don't have live hardware ready and there to instantiate. You want to be able to mock it out. So what I tell them to do is that these subsystems shouldn't count on building the hardware themselves. You should inject already instantiated hardware into these subsystems, and in that way you separate the concerns of having to create the hardware inside the subsystem. If it's done from the outside, then when you create your tests, you can mock that hardware up and then send it into the subsystem, and the subsystem doesn't know or care whether it's actually real hardware or not. So I suggested to just declare these instance variables without instantiating them, and then create a constructor that takes those pieces of hardware and then assigns them as such. And then, so that you don't have to do all of the ceremony of creating from the outside, if we're talking about having this put into a command or some other place, when you want to use the subsystem, since you don't want to have to do this ceremony all the time of creating these things, you can simply create a static method and call it create or factory or whatever, and do the instantiation of the hardware components as you sort of normally would and just return it back. So that's the first thing that I suggested. And what that allows you to do, so let's now go over to the test. So this test has been created, normally, let's look over here. Normally in your folder, you will have a subsystem, and this is where he put his sorter.java class. I've created a test folder sitting under source and created the same directory hierarchy as exists over here so that you can easily identify what it is that you're trying to test. And under subsystems, I created a class called sorter test.java so that we know that this goes with the sorter class. We're going to be using JUnit as our test runner, our test framework, and that's useful because VSCode already has JUnit test runners built into it that will automatically detect that you have tests and will hook up the ability for you to run those tests very easily. So I've created a class called sorter test. I'll come back to this static here because that's a bit of trickery that's required to make this work. But you'll see I have a test decorator here called _test that tells the JUnit runner that this method is a test, and when you run the runner, to pick this up as part of the test suite. So the first test, well, let me back up. So the student, when he created the sorter, he created a there's 3 components required. There's a motor to run the sorter, there's a piston to kick the bad balls out, and there's a ball sensor to detect what kind of ball that we've got. And when he created the class, let's go back here, he created these 2 methods, extend piston and retract piston. And what I suggested to him is, well, what you're really, from a subsystem perspective on the outside world, what you really care about is ejecting balls. The user of this class doesn't really need to know or care about whether it should be extending the piston or retracting the piston. You should just be saying eject ball. So I went on ahead and did that for him. I created an eject ball method where I basically extend it and retract it. And there's some to-dos here about probably delays that he needs to go work on that we probably need to have that's configurable. Not sure, but put a little to-do in there for him. So now what we want to do is we want to test ball ejection, and in particular what we want to make sure of is that as part of ejecting the ball, that the piston is put into the forward position in the act of doing the ejecting. So that is what this test is doing. It should extend piston when ejecting. So first thing that we want to do is we want to mock our 3 pieces of hardware. There is a mocking framework called Mockito, and there's, in the comments to this video, I will put some tutorial places that you can go to look up Mockito. But basically what it does is it will instantiate classes for you with the same public interface as would normally be created if you were to create the class for real. And then it allows you to hook in your own responses to making those calls so that you can predictably know what that class is going to do when you call it without having to have the actual implementation wired up and running, which is what we want. We don't want this hardware to really exist. We want to be able to mock it up and run the sorter and its methods as if the robot was running, but of course it's not. So what we want to do then is mock the Victor SP motor controller, a solenoid, and a digital output. This actually should be input, but he coded it as an output. But for the purposes of this tutorial, it doesn't really matter. We want to mock up these three pieces of hardware. And by the simple act of doing that, now I can call my constructor, my sorter subsystem constructor, and pass in the three pieces of hardware that I just instantiated up here. I can now call eject ball. And now what I want to check is, did the piston hardware device get the set method called on it with the forward constant value? So that's what this verify function does. It's part of Mockito. And so I send to verify the piston mock class, the hardware class that's up here. I use this times variable to signify how many times was something called on this variable. And then the thing that's called is the set command. And what am I looking for in the set command? I'm looking for the double solenoid value of k forward. And this verify command will make sure that that got called once. All I have to do then is hit run test. I have no robot, nothing plugged in. I can run the test, and then when I click the little check mark here, I get my gratification that my subsystem actually can eject the ball and make sure that the piston goes out. Okay, now there are a few things that you need to know about to make this work. First thing is the standard version of WPILib that is coming down for us anyway, by just running the template project creator, is version, I forget the version. Let me go back here and look at it. No, here we go. Under expanded archives, it is version 2018.4.1. I think there is a later version out there in alpha stage, and why I'm not getting it, because we're using the alpha version of the plugin, I'm not quite sure, but anyway, it doesn't matter. This version has a dependency in it for something called HL usage reporting. I think it stands for high level usage reporting, and I think in this version of the framework, WPI has provisions for doing usage reporting when you run your application, reporting back maybe to some central server that of what it is that you're using or whatever. I don't really know what it's for. It's not really important. And what's more, if you run this test without these three pieces of lines of code in here, you're going to get a exception thrown, essentially saying that you didn't have high-level usage reporting set. I forget the exact message, but you'll get something to that effect. So what this code does is this basically nulls it out. There is a null class that implements the high-level usage reporting interface that basically doesn't do anything. And by doing this, you basically fake it out so that you don't get the exception anymore. So anytime that you're calling you're trying to test a subsystem class that you subclassed, you'll need to put these three lines of code in your test to fake that out. I think in the later version, the alpha version, I didn't see this in the code anymore, so maybe WPI or First has removed it and it won't be an issue in the future. Next, so the runner helpers that you get up here, if you run them for the first time, if you create your test class with a little test ampersand in here and you do a build and you click run for the first time, you'll get a new file that's created called launch.test.json. It'll be located in your .VSCode directory. And the reason that it's important to know about this is because when that file is created, these are the configurations. These are the configurations that can be used for JUnit, for the JUnit runner. By default, the default parameter is blank, and the environment parameter is blank. And the reason that that's important is because, at least in our case, we're using network tables to write some values. And so network tables has a dependency on a JNI, a Java Native Interface DLL called ntcore. And if you were to hit the run button with the default file that's created, you're going to get a unsatisfied link exception looking for the ntcore DLL. And that is because the JUnit runner is not configured by default to know where that DLL is. However, you can easily tell it where it is by setting a path environment variable here, and you set it to the JNI extractor under temp, under build for your project. Every project built with the WPI template will have a build directory where all the JNI files are extracted to. So in the act of setting this, that tells the JUnit runner where to pick them up. And secondly, in order to tell the JUnit runner helper which configuration to pick up, you need to put the name, which is identified here, up here in this default parameter location. And you'll need to do it for both the run configuration and the debug configuration so that you can not only specify the run, sorry, I'm in the wrong file. Not only so you can specify the run test helper, but you can also do the debug test helper. Next thing to be concerned with is that in your default build Gradle file, you'll need a couple of bits to add. First thing is that since we're running a test task as part of the build process, in fact, when you run build, the test task will get run by default for you. You can run the task separately and by itself, but when you run .gradle wbuild, you will get the test suite automatically run if there's already tests. As part of the compilation step, though, you don't always need JUnit and Mockito included in your set of dependencies. You only need it when the test step is executed. So if you use the test compile directive under dependencies and you specify JUnit and Mockito, you'll only get those dependencies included when the test test task is run. So you need to be able to identify those two dependencies, and by doing that, they will automatically get downloaded from Maven for you. However, only if the Maven Central repository is referenced. This reference is not automatically put in your build Gradle file from the template. So those are two pieces that you have to remember in your build for testing. Next, and finally, the class path. There's a .classpath file that's created that's part of the standard template, project template. And so one of the things that I was encountering after I had created my sorter test.java file, VSCode was giving me an error down here saying that, well, that's nice, but that file is not part of the class path, so I'm not going to compile it. So what I had to do is I opened up this class path file, and only this entry existed. Well, and these entries down here too. But what this told me as I looked at it closer is that the class path was only picking up source main Java, which makes sense because that's where my main program is. But I needed a way to also tell it, hey, I've got code sitting over here in this test directory. So I essentially duplicated this, and I added the source test Java path, and then also gave it the output of bin/test because we want to keep our classes separate between the two compiled class files. And indeed, if we go over here and we look at bin, I've already run the build on this. I see a test directory, and indeed now I see my sorter test.class. So I know that this got picked up and used, and also the nag window that I was getting here is now gone. So what we demonstrated here is that you don't need a robot to test, so it's easy to get instant gratification. You basically can use JUnit to run your tests. There's a few little bits that you need to make JUnit work, but with Mockito and JUnit, you can run your robot code and test it before you ever have the robot. So I hope you've enjoyed it and find this useful. Thanks for watching.